first stage of the MAV development is the construction and test of the quad-rotor helicopter. Here you can see the quad-rotor helicopter assembled. This is a so-called microcopter. It's a German design, and using an open source diagnostic tool I can pull the sensors and control the motors. First I will show the computerized control of motor 1 and then all of the motors. First I will actuate motor 1 using the computer control. Second, I will actuate all the motors, being careful not to launch the craft. This is motor 1. Now I'll actuate all of the motors. Using the open source diagnostic, I can also pull the sensors on board. As you can see from the open source diagnostic tool, as I tilt the helicopter, its sensors indicate this. Using that data, I can then interpret the data using the single board computing device that I've chosen for the brain and make decisions based on what the sensor data tells me. Here's the single board computer. It weighs about 100 grams. That's about 20% of the maximum carrying capacity of the helicopter. Another important aspect of the work is developing a brain module, and one of the important jobs of that brain is to be able to do obstacle detection and avoidance. To that end, one of the technologies being utilized is an ultrasonic range-finding sensor. This is the sensor. The single board computer, as previously noted, is acting as the brain. Currently, the sensor is connected to the brain, and I've serial connected this to my desktop computer for the purpose of detecting the output signals from the brain. Here's a test of the range-finding sensor. I'm sweeping the sensor around the room. As I hold the sensor closer to the floor, you'll notice the number in the 5th column begins to descend. As I pull it further away, it ascends. Occasionally, sensor noise will occur, necessitating digital signal processing so as to eliminate erroneous data values. Another important element is determining how my brain is going to control the MAV once that happens. The current RC control structure consists of a remote control transmitting packets, the output of which is presented here. As you can see, as I move the remote control dials, the packet structure changes. In order to simulate this same packet structure, but from a computer-controlled source, I've developed a packet generation algorithm which is implemented on the MS-430 wireless sensor module. The MSP-430 will also act as a wireless sensor module to communicate with wireless sensors in the field and transmit this data to the brain module. The brain, the MSP-430. I'll give you an example of what the generated packet from the MSP-430 looks like. As you can see, the MSP430 packet is similar in nature to that generated by the RC packet. Similar enough to fool the helicopter into believing that this is the packet control from the RC. Comparing these two packets on the computer screen, you can see that they line up almost exactly. The next step in the research is determining a flight control algorithm through learning to fly the helicopter in the manual sense, and then emulating this control structure in software.